and colors. In the previous module, we discussed digital images, pixel values, lookup tables, and image histograms. In this module, we'll build on those concepts by exploring how image data are visualized using color. Understanding color representation is particularly important in multiplex immunofluorescence because we frequently work with multiple markers, each represented by a separate image channel. The way we choose to display these channels can greatly affect how easily we interpret the data, even though underlying measurements remain unchanged. We'll also discuss different types of color images, examine how various color maps or LUTs influence image visualization. Let's briefly review the broader learning objectives that connect to this module. How are fluorescence signals stored in an image? And how digital images are represented and how we interpret image data appropriately. Today's focus is primarily on visualization. Specifically, we'll examine how different display choices affect what we see and how those choices can either support or hinder interpretation. By the end of this module, you should have a better understanding of the relationship between image data and image display and how LUT selection can improve communication and analysis of fluorescence images. Before discussing color, let's revisit brightness adjustments. As we learned previously, changing brightness and contrast affects how pixel values are displayed, but does not necessarily alter the underlying image data. This distinction is important because many visualization tools modify appearance without changing the actual measurements. When interpreting fluorescence images, we need to be aware of whether we are viewing raw data or simply adjusting how that data are presented. Brightness, contrast, and color mapping are all examples of display operations that can dramatically alter appearance while leaving pixel values unchanged. There are two major categories of color images that we commonly encounter in microscopy. The first type is a multi-channel or composite image. These images preserve the original data acquired by the microscope. Each fluorescence channel is stored separately, allowing quantitative measurements to be performed accurately. This makes composite images ideal for multiplex immunofluorescence. However, their appearance can vary depending on the software being used, and some programs may not display them correctly. This is because the second type, an RGB image or red, green, blue image, is the more common type in most cameras outside of microscopy as well. RGB images are designed primarily for viewing and sharing because they have a standardized appearance, they are easy to display, and consistent across different computer monitors. The downside is that the conversion from multi-channel data to RGB often results in loss of information. Original pixel values may no longer be recoverable, making RGB images unsuitable for many quantitative analyses. As a general rule, perform analysis using the original multi-channel data and reserve RGB images for presentation and communication purposes only. Now let's discuss selecting an appropriate lookup table or LUT. Different LUTs have different strengths and weaknesses. First, grayscale. Grayscale is simple, familiar, and universally understood. It is also accessible to people with color vision deficiencies. However, it can sometimes make subtle intensity differences difficult to appreciate, especially at the extremes of the intensity range, such as when something is black and something is maybe not quite as black. Next, the JET lookup table. JET became popular through software such as MATLAB. In JET, low values are shown as blue, intermediate values as green, and yellow and high values as red. One advantage of JET is that it highlights differences across the intensity range and makes extreme values very noticeable. However, JET has important drawbacks. The color transitions are not perceived uniformly by the human eye and is not colorblind friendly. This can sometimes exaggerate differences that are not truly present in the data. Finally, Viridis. Viridis was specifically designed to provide a more perceptually uniform representation of data. Research suggests that viewers interpret changes in Viridis more linearly than many traditional color maps. Viridis is also colorblind friendly, making it a strong choice for scientific visualization. While no LUT is perfect for every situation, Viridis is increasingly recommended for displaying quantitative image data because it minimizes visual bias and improves accessibility. In this exercise, we'll apply the Viridis LUT to a fluorescence image. First, download the LUT collection from this GitHub repository. After downloading the zip file, extract its contents. Next, in QuPath, we'll open the fluorescent cells image again and send the image region to image.j using the image.j command. Accept the default settings when prompted, and within image.j we'll then navigate to the image in the menu bar and then color and select edit LUT. We'll choose open within the LUT window and locate the file named viridis linear-lumen.lut and load it. Once applied, compare the appearance of the image to the default visualization. Pay attention to how the same underlying data may become easier to interpret depending on the LUT that you've chosen. Remember that applying an LUT changes the visual representation, not the measured fluorescence intensity values themselves. I'll now pause here to give you a chance to try this exercise yourself. I'll now demonstrate how to perform these steps in QuPath repository. Unlike before, when we were installing QuPath, we can see all of the files within this GitHub repository, and we'll download them all by creating a zip file. We'll see that the zip file has been downloaded. Remember, this is now in our downloads folder on this computer. We'll select the zip file and select extract all, and save it in a location we can access later. In my case, I'm going to save it to the desktop. Once we've extracted all, we can now go into the folder and see all of the files within it. Now we're back in QuPath with the fluorescent cells sample image open. We can go to the image.j commands in the toolbar and select send region to image.j. A window will pop up with some parameters of how we want to send this, but we'll keep them at the default and click OK. You can see the image is now opened in image.j with the image.j window. We're going to have to first go to colors and split the channels. This now produces an image window for each of the channels of our image. We're going to change the image window of one of these images. We'll select it, go to image, color, and edit LUT. We can now see that for each pixel value from the top left being 0 along the row and going all the way down to the highest possible pixel value of 255 for this 8-bit image, that we can have a color for each pixel value. We're going to open the Viridis lookup table by clicking open and selecting the viridis-linear-lumen.lut and click open. We can now see that the pixel values have been reassigned a new color which maps onto the Viridis lookup table. We can do this for each channel of our image by clicking OK first and then selecting the image and going through the steps again. Like so. Let's review the objectives of this module. Throughout this module, we've continued building our understanding of digital image interpretation. We've reinforced the distinction between image data and image display, discussed different types of color images, and explored how lookup table selection affects visualization. These concepts will become increasingly important as we work with more complex multiplex immunofluorescence datasets containing many image channels and markers. To conclude, here are the key take-home messages from this module. First, image appearance can often be changed dramatically without altering the underlying pixel values. Second, multi-channel images preserve original microscope data and are generally preferred to quantitative analysis. Third, the different LUTs can emphasize different features within an image while displaying the same underlying data. And finally, choosing an appropriate lookup table is important not only for accurate interpretation, but also for accessibility and scientific communication. Keeping these principles in mind will help ensure that fluorescence images are displayed clearly, interpreted correctly, and communicated effectively in both research and clinical settings. Thank you, and join us for the next module on dimensions.